All right, this is the second part of my video on an introduction to functions. It says here, graph each function. The first one, number 4 here, is f of x equals square root of x plus 1. So at this point, the only technique we really talked about that would help, that we've talked about that would help us here would be plotting points. And so let's go ahead and make an XY chart. And again, I think I'll start with 0, just keep things simple. So if I plug in 0 here, I get the square root of 0 plus 1, which is the square root of 1, or 1. So when I plug in 0 for x, the corresponding output is 1. So let's go ahead and plot that point, 0, 1. And might as well go up to the next number, 1. When you plug in 1, it will be the square root of 1 plus 1, or the square root of 2, which is about 1.4. So that goes about right there. And I'm going to go ahead and plug in negative 1. I want you to notice, if you take the square root of negative 1 plus 1, you're taking the square root of 0, and that's just 0. And so that would be that point there. And notice if I plug in something to the left of that, like negative 2, we'd be taking the square root of negative 2 plus 1, which is going to be the square root of negative 1, which is imaginary. Now when we're dealing with functions, I always tell my students, you got to keep it real. Anytime we're graphing on the xy axis, we're dealing with real numbers. And so we can't plug in any number that's smaller than negative 1. So let's go back on the other side. Now I could plug in 2 and I'd get the square root of 3. We can be a little bit more careful with our choices. In fact, the square root of a nice perfect square would be better. Like the square root of 4 would be nice, and that would happen if I put in x equals 3. And so the square root of 3 plus 1 is the square root of 4, which is 2. So 3, 2 is on the graph, and in fact the function looks like that. And I call this the ET function. You can see how it's like the ET long finger starts at a certain point and goes off to the right, in this case. All right, let's go ahead and look at number 5. G of x equals x cubed minus 2. And again, I'm going to go ahead and make a table of values. And I'll start with 0. 0 cubed minus 2, that's just going to be negative 2. So let's go ahead and plot that. And let's go ahead and throw a 1 in there for x. 1 cubed is 1, and 1 minus 2 is negative 1. So we get the point 1, negative 1. Let's go ahead and plug in 2. 2 cubed is 8. 2 times 2 times 2. Minus 2, you're going to get 6. And we get that point there. And actually, if you plug in 3, you're going to get 3 cubed, which is 27. And that's going to take us off the grid. So I think I have an idea of what's going on this side. It's going to look something like that. So let's go ahead and choose a negative number like negative 1. And negative 1 cubed. Now be careful, when you multiply 3 negative 1s, you do get negative 1. Minus 2, you're going to get negative 3. And so that'll be that point. And let's do one more, negative 2. When you cube negative 2, you're going to get negative 8. And negative 8 minus 2 is going to be negative 10. And so we have the point negative 2, negative 10, which is a little bit off the grid. So our graph's going to look something like this. I actually called this one the John Travolta graph. Anyway, let's go ahead and move on to number 6. So it says here, use the given graphs to find each of the following function values. All right, so let's see, I want to do something here. So if you look at A, notice 0 is your input, or your x value. So what I want to do is look on the graph where my x value is 0. So notice x is 0 right here where I put this little red x. And if you look on our graph, the line, the point that has an x value of -1, that's this point here, is the point 0, -1. And so if my input is 0 on this function, the output is -1. And we can do the same thing with b. You might try it before I do. And so when x is -1, that would be this point on the graph. That's the point -3, -1. So when the input is -1, the output is -3 for this function. Now, there's another way I like to show students. Let's go ahead and look at this graph right here. And I want to ask you an important question. When you're reading a graph, is it the x values you care about, or is it the y values? What really matters when you're reading a graph? Well, you can see on this graph the x values are just the year. And actually, let me finish this up. So if 200,000 is right there, you can see, we'll say these are median home prices in the Dallas area. And so you could see over this period of time, the prices were rising. So there's a point here, that would be the point 2016, and we'll just call it about $210,000. And so you can see in 2017, we're about here, and now you're probably maybe at $215,000 or something a little bit higher than 210,000. But you can see what we really care about, and as we see this line here going up, it's the y values that we care about. And really, it's the y values are just the height of the graph. And so these heights are the 210,000 and the 215,000. And so let's go back to what we were just doing and think about the y values as the height of the graph. So when I find f of 0, what I do is I look at where x is 0 and I say, what's the height of the graph? Well, notice the graph is down 1. So f of 0 is -1. F of -1, well, the question is, what's the height of the graph when x is -1? Well, you can see the graph is down 3. And so f of -1 is -3. All right, so now I'd encourage you to find the other 3 here. All right, so let's see how you did. On f of 2, when x is 2, what's the height of the graph? Well, notice we're up 3 here, so f of 2 is equal to 3. Now again, we know that means that the point 2, 3 is on the graph, but you could really do these either way. G of 2, when x is 2, now notice we're on the g function. What's the height of the graph? Well, it's down 1 at that point, so g of 2 is -1. And what's g of 4? Well, when x is 4, the height of the graph, well, we're also down 1. All right, I'm going to give you one more since those last two actually were the same. So notice this is the graph of a function, but we got the same output twice here. It's still a function. What if I asked you to find g of 5? Well, when x is 5, what's the height of the graph? Well, it's up 2. All right, so hopefully that'll help you to evaluate functions by looking at a graph. Let's go ahead and move on to the next slide. All right, so we're going to talk a little bit more about domain and range, but this time we're looking at equations. So notice it says the implicit or implied domain of a function includes all values of x for which the output is a real number. Now, I really didn't need to put the word implicit or implied here, but really that's what we're dealing with here. So let's go ahead and look at these. So it says for a linear function, the domain is going to be all real numbers. Well, when you look at lines, unless you have a special case, which is a vertical line, your domain's always going to be all real numbers. and we'll talk about, when we get to number 1, we'll talk about that again. For quadratic functions, the domain's all real numbers as well. The only one where we're going to have some kind of restriction is when we have rational functions. So notice it's all real numbers, or our domain is all real numbers, excluding any values of x that cause the denominator to equal 0. All right, so let's go ahead and I want to go ahead and write the all real numbers actually 3 more ways. So first of all, this is what we call set notation, and that's one way, or set builder notation. That's one way we can write all real numbers. The one we're going to use most frequently is interval notation. That basically says everything from negative infinity to positive infinity. And finally, we can also represent this set of numbers, all real numbers, on a number line, where we just shade the whole number line. All right, so again, normally this is the form we're going to use, interval notation, when we give answers for domain and problems like what we're about to do. All right, so it says on number 1 here, find the domain of each function, write your answer using interval notation. So I was saying that for linear functions, the domain is all real numbers. Now remember, we said a function, for a function, each input has exactly one output. So basically, we want to know what numbers can we plug into the function. Is there anything that we can't? When we say the domain's all real numbers, we're saying we can plug in any value as an input. So I'm going to do a couple here. F of 0 would be negative 2 times 0 plus 3, which is 3. If I plug in, we'll say 1, I'd get negative 2 times 1 plus 3, which is 1. Now think about what this function does. You basically plug in an input, you're going to multiply that input by negative 2, and then you're going to add 3. Now there's no number that I can't multiply by negative 2 and then add 3. So I can plug in anything here. So that's the idea, which means our domain is all real numbers. Now notice on number 2, this is a rational function. And so again, we said rational functions are the ones, at least the only ones for now, they're going to have a domain that's not all real numbers. And so let's go ahead and plug in 0 here. In fact, a lot of times students think that 0 is not part of the domain here, that I can't plug it in. But this would just equal 0 over negative 5, which is 0. So 0 is not a problem. The problem is with fractions, my denominator can never be 0, because that makes my fraction undefined. Notice if x were 5, then we would have a problem. So normally I would list my restriction, x cannot equal 5, and then the domain is everything else. So we're going to go from negative infinity up to 5, and we're going to use a parenthesis to indicate that our domain doesn't include 5, and then we're going to go from 5 to infinity. So basically that's how we write the domain, where we're just excluding one value. In other words, what I'm saying here is I can plug in any number as an input into this g function except for 5. It turns out it's only the values of x that cause my denominator to equal 0 that I have to throw out. Everything else is good as far as our domain is concerned. So on number 3, notice this is quadratic because of the x squared. The highest power is 2. And so this function has a domain of all real numbers. Now number 4 is another rational function. And so I need to find my restricted values. That would be the values that cause our denominator to equal 0. Well, the easiest way to do that is let's set our denominator equal to 0. This is a trinomial, and you should know how to factor this. Let's go ahead and get it set up. So basically, we're looking for two numbers that multiply to negative 12 and add to 1. And so I'll go ahead and set up a little chart here. Now the factors of 12 are 1 and 12, 2 and 6, and 3 and 4. Now since these numbers need to multiply to negative 12, one of the numbers has to be negative. And since the two numbers need to add up to 1, that means the bigger number should be positive. And so the smaller ones will be negative. Notice negative 3 plus 4, that's the one that's going to equal 1. And so we'll plug in a minus 3 and a plus 4. And so we've factored this polynomial, or this quadratic function or equation, into x minus 3 times x plus 4. Those are our factors. And the next thing we do is set each of those equal to 0. And when we solve for x, we get 3 and negative 4. So those are the solutions to this equation. Those are the values that cause our denominator to equal 0. And so those are our restricted values. Our domain will include everything else. So if I actually graph this, basically it would be the whole number line, and it would exclude negative 4 and 3. And so we're going to go from left to right. That's how we always write interval notation. We start out in negative infinity land, and we go to negative 4. And then we're going to go around negative 4. That's why we're using parentheses there. Then negative 4 to 3, and we're going to skip 3 and go from 3 to infinity. So usually interval notation looks pretty nice when it's written. It's short and sweet. Not so much the case here, but hopefully you get the idea. That's just every real number except for 3 and negative 4. Now if you look at number 5, this is the absolute value function. It's not one of our, well actually it's not a rational function, and so at this point we know it's going to have a domain of all real numbers. Now you may recall the graph of absolute value function like this is V-shaped, and you can see it goes forever left and forever right, and so the domain is all real numbers. But for now, just because it's not my one where I have a restriction, that's rational functions, we're going to say all real numbers. And the same thing's true on number 6. This is a cubic function, which you may have some experience with. The graph will actually look something like that. But again, our domain is all real numbers. And for now, we're just going to say that because we know if it's not rational, all of our other functions we're working with right now have a domain of all real numbers. And all that really means is I can plug in any real number as an input into these functions. All right, let's move on to the next page. It says determine the domain and range for each function. So here's how we're going to do this. For the domain, now remember that's the set of all the x values of the functions. Really, it's all the x values of the points on this line. And so we're going to go, since the x-axis goes from left to right, it's horizontal, we're going to go from the leftmost to the rightmost point, and we're going to look at x values. Now notice there is no leftmost point, there is no rightmost point, and our points are hitting everything in between. There's no holes or gaps or anything. And so our domain is all real numbers. What about the range? Well, again, this is my lowest. Actually, you can see I don't have a lowest point. And as you go to the right, this is going up. I don't have a highest point. And so the range is also all real numbers. Now, I didn't spell this out. With the range, we're looking at y values, and we're going along the y-axis. Really, it's the y value of the points on our graph. So we want to go from the lowest point to the highest point, and we're looking at y values. So there is no lowest or highest point, and again, our points hit everything in between, and so our range is going to be all real numbers. Go ahead and look at B and think about what the domain and range is, and see if you can figure it out, and then watch the video. All right, so for the domain, I want to go from the leftmost point to the rightmost point. Now notice at the leftmost point, the x value is -2. With domain, I'm looking at x values. And then my rightmost point is right there, and the x value there is 3. And so my domain, and notice these points are on the graph because we have solid dots at those endpoints. And so it goes from -2 to 3. What this is really saying is if you look at all these points, they have x values between -2 and 3. I mean, like here, this one here has an x value of 0. Here, this point has an x value of -1. All my points will have x values between -2 and 3. Now, let me erase my little dots here. And now let's look at the range. So notice we do have a lowest point here, and the y value there. Now remember, we're looking at y values because it's range. The y value there would be -3. And we also have a highest point right here, and the y value there is 6. And so our range goes from -3 to 6. And since both of these points are on the graph, we're using a bracket to indicate these x values are part of the set. There is a point right here that has an x or a y value of -3. And so that's why we're using a bracket. All right, I would encourage you to try C and D and then watch the video. All right, on C, you can see that we have no leftmost or rightmost point, and again, everything in between, there's no gaps or anything, and so our domain is all real numbers. What about the range? This one's a little bit interesting. In fact, don't all of our y values equal 1? And so how do we write that? That would just be the set with 1 in it. Notice we use braces because this is not an infinite set. We can actually list the one and only output for this function. So for D, you can see you should see that the domain is all real numbers, because again, you have no leftmost or rightmost point, and you're hitting every point in between. There's no gaps or anything. So what we're saying is, if you look at all the points on this graph, x can be any real number. Let's see, hold on a second, I need to erase this one here. If you're going from lowest to highest and you're looking at the range, notice there is no lowest point because you can see on the right here, this thing goes down forever, but there is a highest point right there, and the y value there is 2. And so our range goes from -infinity to 2. All right, and that's the end of this video.